Yeah, thank you for the introduction. Okay, so these figures are just to show that the problems are real. Real factory floors have become the victims for cyber crimes. And more importantly, comparing to the traditional attacks that are targeting at consumer systems, these attacks are different in the sense that attackers are not only trying to make profits, but more importantly, they want to cause physical damage. They want to cause safety hazards. Learning from the prior incidents, we know that the PRC actually is a major attack vector. So PRC stands for Programmable Logic Controller, which is the core control unit for the entire factory floor. So safety violations actually can be introduced into the PRC code either by accidentally, by mistakes, or intentionally by attacks. Either way, the problematic code will eventually cause damage to the infrastructure. So knowing this, a great many of prior work actually has aimed to automatically detect the safety violations in individual PRCs. However, a common limitation of the prior work is that they overlooked an important fact that the industrial control system is actually a highly collaborative environment. PRC is never working alone. So this photo actually shows our testbed. It's called Smart Testbed. It's a precise miniature of automotive production line. It's actually developed by domain experts from Rockwell Automation, which is the #1 manufacturing vendor. As you can see, even within this small-scale system, it has already included a lot of different components. It has a PRC, and also has multiple CNC machines, each of which is also equipped with a small PLC. And we also have multiple robots, which are programmed to perform different actions. Aside from all those programmable units, we also have some non-programmable units. For example, here we have a circular conveyor belt. And we also have pallets that are moving on top of this conveyor. So these pallets are used as containers to hold and carry these parts and deliver these parts to different CNC machines for processing. As a result, PRCs are actually intensively communicating and collaborating with all the components on the factory floor. And the PRC code is actually driven by the external events from other machines. What that means is that in order to be able to detect the safety violations by testing PRC code, we also need to take all the external inputs events into consideration. So essentially, this is a code testing problem for event-driven programs, which, however, is a well-studied problem in other domains. For example, Android applications or web applications. In order to understand how to test the PRC code, which we can just first learn from this prior work. For example, if we want to test an Android app, what we can do is we can first run it in an emulator, and then we can model and simulate input events as a sequence. To improve code coverage, we can further rearrange the order of the events to generate different permutations. So all the sequences will be used to drive the program to run and eventually help us to find the bugs. Essentially, we can do the same thing for testing PRC. Right? So we can first simulate the PRC execution, and then further simulate input events. Of course, we can rearrange their orders. However, in practice, what we have noticed is that just rearranging the order of the events is not sufficient to test the PRC code. What we have observed here is that two event sequences of the same ordering may or may not cause a safety problem because their timings are different. To give you guys a more concrete idea, let's take a look at this running example. This is actually a real-world problem that we have discovered from our testbed. So here we have a conveyor belt, which is sending an empty pallet to a cell. So this cell consists of 2 CNC machines and a robot. The entire system is controlled by a PRC. So once this pallet has arrived at this cell, it will be blocked by a stopper. During this process, 5 events will be sent to PRC. And once PRC has received all these 5 events, it will trigger 2 actions. First, it will update the state of the part, which is actually stored on the part. Once that is done, PRC will receive a signal, event 6, update complete. The second action is to request the robot to pass a processed part from the CNC machine to the pallet. And once that is done, the PLC will receive event 7, part at conveyor. So once both of these 2 events are true, then PLC knows that now the pallet has already been loaded with a part. It will then retract the stopper to let it go. So notice that here, this event 7, part F conveyor, actually has another purpose. So when it is also used to control the robot. When the signal is on, the robot will always wait at the conveyor belt. Only if it is turned off, meaning the part has already left the cell and the conveyor belt is now clear, then the robot can move towards a CNC machine to prepare for another delivery. However, in practice, for the sake of a throughput, we don't want the robot to always wait at the conveyor belt. Instead, we want it to move towards the CNC machine in advance, right, to save some time for another delivery, regardless of whether the conveyor belt is cleared or not. And therefore, we will proactively terminate this event 7 within 0.5 seconds. Nevertheless, this does not cause any problem in normal situations. Right? The system works fine and it conforms to our predefined safety rule, which requires that the time duration between pallet arrival and pallet departure is no greater than 30 seconds. We further formally define this safety rule using TPTL, right? Timed propositional temporal logic. However, if somehow the event 7 happens very early, for example, because of the increase of robot speed, then what can happen is that this signal will terminate prematurely, right? Even before the occurrence of event 6. In this case, there's actually no time window when both of these 2 signals can be true. And even if the pallet has already been loaded with a part, the PLC will never know and it will never retract the stopper to let the pallet go. This will definitely violate our safety rule. To detect such a problem, let's first just try the traditional way, which is to generate event sequences based on different ordering to test the PRC code. So for example, we can create a sequence like this, right, from event 1 to event 7. So in this case, everything works fine. Then we can rearrange the order of the events, right, to 5, 7, 6. So in this case, something wrong happens. So this is actually exactly the same as what we have seen in the last slide. However, such a sequence may not always be able to cause this problem. For example, we can create a third sequence, which actually shares the same ordering as the second one, 5, 7, 6. However, since event 6 actually happens before the termination of event 7, everything still works fine. So this actually explains that pure ordering-based event sequence generation cannot sufficiently help us to discover the safety violations in the PRC code. To solve this problem, we proposed our solution, right, VetPLC, which can create timed event sequences. To do so, we first perform program analysis on PLC and robot code to extract the causal dependencies among the events. So this can help us to rule out the impossible permutations and reduce search space. And then we further resort to the runtime data that is collected from our physical test beds and perform data mining to extract timing invariants for events. So these timing invariants are corresponding to some certain machine operations. So eventually, these timed event sequences can help us to perform testing. Now let's see how we actually apply VetPLC to our running example. So first of all, we want to perform program analysis in order to extract the causal dependencies among events. However, if we just look at the PLC code, what we can see is a bunch of independent if clauses, so which are effectively the event handlers in the PLC code. We do not really have any knowledge how these events are related to one another. To address that problem, we further look at the collaboration between a PLC and a robot. So in this case, when the part at conveyor is false, in other words, the event negative part at conveyor is received, the PLC will send a signal to DI0, which is the digital input 0 at the robot side. Upon receiving this signal, the robot will trigger a routine in which it will first perform some robot movements, and eventually it will send a signal to the digital output 2, which is then mapped back to the part at conveyor event at the PLC side. So now we know that there's actually a causal dependency between these two events. And by further performing data mining, we know that the time duration between these two events, is actually a soft invariant, which is actually corresponding to the time cost to deliver a part. And furthermore, if we consider the speed reconfiguration for the robot, we can also compute the theoretical bound for this delivery time. Then by digging into the robot code further, we know that the event 7 actually can only last for 0.5 seconds, which is actually a constant hard-coded in the robot program. And again, by performing data mining, we know that the time duration between event 5 and event 6 is also a temporal invariant. So there are some technical details. Due to the time limit, I just do a flyby. So in order to model the causal relations among the events, we actually introduce this timed event causality graph. So to build this graph, we actually borrow some idea from the AND/OR graph, and eventually we perform context-sensitive, flow-sensitive, interprocedural data flow analysis. So the detailed algorithm is in our paper. And in terms of the data mining, we also follow some existing approach. Particularly, we follow the synoptics approach to determine the qualitative relations between events. And further, we leverage Perfume's algorithm to determine the quantitative relations between events. And eventually, for this case, we can discover 3 temporal invariants. So now that we have built the graph and we have extracted the temporal invariants, we can leverage this knowledge to create timed event sequences. Particularly for those independent events, for example, in this case, the first 5 events, which do not bear any relations, we can actually arrange them in any order. So when 5 events are all received, the time is t. And then further, by leveraging the knowledge from data mining, we know that the event update complete actually happens between time t plus 15 to t plus 20. And further, in order to encode this timing knowledge into event sequences, we discretize the continuous time range into multiple slices. And for each slice, we will create a version event. So for example, here, we can discretize this time range into two slices, and therefore create a 3-version event. So in this time sequence, we only need to pick one. And we can do the same thing for another event, part at conveyor. The only difference is that since we know this event only lasts for 0.5 seconds, so we will proactively terminate this signal accordingly. So here we actually can create this event sequence that can actually cause the safety violations that we have discussed. However, another question remains here is how do we discretize the time range in a proper way? So we will answer that in our evaluation. So our evaluation is actually performed using real-world physical test beds. We actually applied it to 2 different test beds. One is a smart test bed, the other is the fish technique, which is a smaller but more complex test bed. We also have applied VetPLC to 10 different real-world scenarios in order to detect the real-world problems. So the first question we want to answer in our evaluation is how many event sequences can actually be created using different techniques. So this chart shows the result. So the red curve is the baseline, which represents the total amount of event sequences that can be created using state-of-the-art technique, or sequence. Right? So all sequence consider only the event ordering, but it consider all possibilities. When we further apply program analysis to remove the impossible permutations, we call it a VetPLC sequence, then we can reduce its amount from the red curve to the green curve. Furthermore, when we apply time discretization, this amount will be increased. It will be increased from the green curve to the orange curve to the black curve and eventually to the blue curve due to different granularities. So as you can see, so this graph shows that the time discretization actually increased the amount of generate sequences to a large extent, especially with the highest granularity. However, since we have already applied the program analysis to rule out the impossible permutations, so the time discretization with a median granularity, in other words, this black curve, can still give us some reasonable numbers. So in the end, we perform a comparative experiments between state-of-the-art and VetPLC to see whether we can find real bugs. So for state-of-the-art technique, we have adopted 2 algorithms, OR sequence and VetPLC sequence. And for VetPLC, we choose to still go with 3 different parameters for the granularity levels. The result is promising. So while the state-of-the-art pure ordering-based event sequence generation cannot help us to detect any safety violations in our test beds, VetPLC with different granularity selection can always help us to detect those problems. And furthermore, we noticed that when we apply time discretization with different granularities, the discovered error triggering ranges are also different. For example, in scenario 1, when we divide the time duration into 2 slices, then what we can see is the problem may occur only when the robot is running at its maximum speed. However, if we improve the granularity and divide the time range into 5 slices, then we may know that as long as the speed of the robot is greater than 550, then the error may occur. So in general, with higher granularity, we may get more precise error triggering ranges for the discovered problems. However, in practice, empirically, we also noticed that the time discretization with a median granularity can already give us some reasonable results. And not to mention that the amount of a generated sequence is also acceptable. So to sum it up, so we have studied the real-world ICS testbeds and got very important insight. Right? So real-world PLC is event-driven and timing sensitive. To detect the safety problems in such PLC, so we developed a system called VetPLC, which can automatically construct timed event sequences. And the result is promising. So VetPLC outperforms state-of-the-art and can detect the hidden safety problems that cannot be discovered using the prior techniques. So with that, I conclude my talk, and I'm happy to take questions.
Great, thank you. I'm Hao from UC Davis. You mentioned that you used data mining to find the timing information. Now, do you use that as a ground truth, or do you use that as a starting point, but you're going to find the exact timing later?
We actually use that at ground truth.
Okay, so then my question is that because it's data mining, you may not have observed all the states.
That's true.
Will this cause false positive or false negative or both in your approach?
So I would say it's generally a challenging problem, the coverage problem. So for us, it's a best effort. And also, our focus is to find out the timing invariance that is related to the machine operations. Okay. And in our case, those there's a limited set of machines. As long as our system goes through all those critical steps for the machine operations, then we can guarantee the discovery for those timing invariants.
So when you say guarantee, which part do you guarantee?
So for example, we want to look for the time cost to deliver a part. For example, as long as we, in our data mining, we always go through that path, then we can always observe that behavior.
So assuming that your data mining is perfect, then you guarantee that the safety property will never be violated.
That's true.
Thank you.